The first one here actually isn't that tough. What do we have to do to solve this one to start out with? Yeah, we have to isolate the exponential. So we're going to add 120. So this is 5 times 32 to the 4x minus 6 equals 5,120. And then, no, you can't combine that. You have to divide by 5 to get rid of it, yes. Yeah, you can't combine it because the 32 is to that power and the 5 isn't. So you got 1,024 here. Then what? To get rid of 32 to the power of something, you do log base 32. Log base 32 cancels out the 32. You've got 4x minus 6. What is log base 32 of 1,024? It's 2. The way we would find that on our calculator, of course, 32 squared is 1,024. But the way we would find it on our calculator is log of 1,024 divided by log of that base, log of 32. Gives us 2. So now 4x minus 6 equals 2. We know, what's that? Add 6, very good. 4x equals 8, and then divide by 4. X equals 2. How many of you had that? A couple of you? Good. Did anybody get an answer for the second one? Okay, let's take a peek at this. This one could be done by just finding all those logs and using the numbers. The problem is the round off errors. There's a very good chance it's not going to come out. So let's look at our rules of logs. Now, there's not a whole lot we can do over here. Log of 2 plus log of x. But over here, 512 is 2 to the power of 9. Over here, the 2 log 4, I'm going to adjust that a little bit. I'm going to make that log of 4 squared. On the left side here, again, there's nothing to change. Log of 2 to the power of 9, that's 9 times the log of 2. Now, you might say, why did I go the other direction here? Well, 4 squared is 16, right? And I did that because 16 is 2 to the power of 4. So that becomes this is 9 times the log of 2. This is 4 times the log of 2. We haven't done this before, but 9 logs of 2 minus 4 logs of 2 is just like having 9x minus 4x. That's going to be 5x. So this is going to be 5 log of 2. Well, now what would we do to solve this for x? We get the log of x by itself by subtracting log of 2. Subtract another log of 2 over here. Log of x equals 5 minus 1 is 4 times the log of 2. Now I do have to go the other direction. Log of x equals 4 times the log of 2 is log of 2 to the power of 4. I do 10 to the power of to cancel out the log on each side. X equals 2 to the power of 4, or x equals 16. What do you think? Pretty tricky? Okay, well, we left off last time talking about decibels. And we hinted on standard powers of dBms and dBmVs. So here's what I would like to present you today. What is the power? Find the standard power for an antenna with signal level of 12 millivolts. So I'm going to give you guys a minute to figure that out. What's your formula? $20, there's what I was looking for. 20 times the log of 12 millivolts over 1 millivolt. Gives us 21.58. What's our units that should go on here? dBm. There you go. Okay. Find the signal level for an amplifier with standard power gain of 8.75 dBm. What formula? Okay. 10 log, and it's going to be voltage over 1 millivolt, or sorry, wattage over 1 milliwatt. How did I know that it was wattage instead of voltage? It's dBm. dBm means we're looking at milliwatts. So now we solve, we're going to divide by 10. So 0.875 equals log. I'm just going to put it as watts. I can get rid of the 1. I just know that's going to be in milliwatts, right? Then what? 10 to the power of, right? 7.5 basically equals our power. So that's 7.5 milliwatts. What do you think? Good stuff? Maybe? Make it stop? How about this? We have an antenna. And coming in off the antenna, we measure the signal level as 1.2 millivolts. From that antenna, we go through 180 meters of cable to get to our first device, which is an amplifier. This amplifier is a plus 12 dB amplifier. Then we go through a splitter. Part of the signal goes one way, part of the signal goes to where we're going with it. This splitter you guys have gone through splitters, there's always one low resistance and one high transmission, one low transmission. The one that we're using here is a let's just go with a 5 dB loss. So negative 5 dB. It proceeds from there. By the way, there's 30 meters of cable here and 10 meters of cable here. Proceeds from there to a plus 10 dB amplifier through another 30 meters of cable to our device. Whether it's a television or whatever it is we're using, that's our device. I want to find the signal level at our device. What we're going to do is we're going to start with the signal level at the antenna, and we're going to convert that into dB. So 10 or 20? 20 because it's voltage. Log of 1.2 millivolts, that doesn't need to be changed, over 1 millivolt. So 20 times log of 1.2 is 1.584. So it's dBmV. We're just going to write it as dBmV like that. A decibel is a decibel. It's just we always put the MV on it to specify that it was calculated from a voltage measurement, a signal measurement. Now we need to know the gains and the losses. We have gains of 12 and 10 here. So to this, I'm going to add 12 and add 10. That puts me at 23.584 dB. There are two losses here. One of them is the negative 5 dB on the splitter. Can anybody tell me what the other loss is? Cable, let's assume that's coax. You know what the loss is in coax cable? Nine dB per 100 meter. So how many meters do we have there? 180 plus 30 plus 10 plus 30 is 250 meters times 9 dB per 100 meters gives us minus 22.5, right? Is that correct? Everybody see how I did that calculation? It's actually a measurement conversion. I had meters, and I converted it into dB by using the 9 dB per 100 meter conversion. So the meters cross cancel out. 250 times 9 is 2,250 divided by 100 is 22.5. So we subtract that. We end up, I believe, with negative 3.916 dB. So that's what we get to this point with. What do we got to do now? Convert it back into a signal level. So 20 log our voltage over 1 millivolt. So we're going to take that negative 3.916. What are we going to do with it? Divide by 20. Gives us a negative 0.1958. And then, 10 to the power of. So, in fact, I can just do this. You've got a 10 to the x key on your calculator with the log. So 0.637 millivolts is my voltage. So 0.637 millivolts or 637 microvolts, however you want to write it. What do you think? Let's do a little bit different setup. Let's say this is a plus 18 dB. Let's say we're losing 9 dB here. Into a plus 12 dB. Let's give this 20 meters, 10 meters, 50 meters, and 120 meters here. Still negative 9 dB per 100 meters. But let's say this. We need 0.9 microvolt signal level here. What do we have to have for a signal level coming in off the antenna to achieve a 0.9 millivolt signal level? I'm going to let you guys look at this, see if you can work that backwards. So we've got to work this backwards. So we start out with what this level is here. That is going to be 20 log of 0.9. Oops. Did I really put that on 0.9 microvolts? Wow. How about I put it as 900 microvolts? That's probably a little more reasonable. So let's just work through it together. I'm not going to make you go back and redo it. 900 microvolts is 0.9 millivolts. That's going to be 20 times log of 0.9. Gives us negative 0.915. That's dB, and of course, from the millivolts. Now here we've got to work everything backwards. We're going to lose for the cable, so we've got to add back in what the cable loss would be. How many meters of cable are there here? 200. 200 meters times 9 dB per 100 meters is 18 dB. So we have to add 18 to get our original signal. We also have to add the 9 that would be lost. So that ends up being at 26.085 dB right now. Now we have to subtract all of our gains. Well, we've got the 18 and the 30 amplifiers, don't we? Or 18 and the 20 amplifiers. Minus 18 and minus 20, that's going to put us at negative 3.915 dB. I don't know why I put 20 down there. Yeah, it should be 12. Thank you. I kept thinking 30 because 18 and 12 make 30. So we've got negative 3.915 dB. Now we have to convert that back into a signal level. So 20 log voltage over 1 millivolt, divide by 20, and then do 10 to the power of, I'm going to do this in the calculator here, negative 3.915, divide that by 20, then 10 to the power of, gets 0.637. Millivolts. So you need to have 0.637 millivolts coming into the system. What do you think? Okay, so there's obviously a test coming up tomorrow. I told you that on Monday. So anyway, you guys have, remember you got the capacitor charging and discharging. We got the inductor increasing and decreasing current. You've got the time constants. You have logarithmic and exponential equations. And of course, you've got now this power stuff, the dBs. It'll just come to you. Some practice, by the way, in that big packet, page 464 through 465. 1 through 10 is on the power stuff. Okay. What we have to do there for that power gain is we're actually going to be looking at a voltage and not a wattage. So we have a 16 ohm resistor and we need to be developing 650 milliwatts across it. That's 0.65 watts. Power can be either current times voltage, or it can be current is voltage divided by resistance. So voltage squared over resistance. So what we have here is that 0.65 watts equals voltage squared over 16 ohms. We're going to multiply by the 16. Yeah, bless you. Then we have to square root that. So we need to produce a voltage of 3.225. So we take that, but of course that is 3,225 millivolts. Now we need to take that with, we have the amplifier that is gaining so that's going to be the voltage lost on the, I'm make sure I'm reading the right problem here. Okay, so I've got that, so I need them to turn that into a power level. So it's going to be 20 log 3,225 over 1. So I get 70.17 decibels. It's got an amplifier of 26. dB, so I'm subtracting off the 26.99. which is going to put me at what, 53.18 dBs. So that's the input power coming into it. That's the input power that has to be coming in. The input resistance is 16 kiloohms. To determine the input voltage needed. So what I'm going to do is I'm going to convert that 53.18 dB into a power. So it's 53.18 divided by 10. Oops, should be 43, not 53. Sorry, 43.18 divided by 10. And then 10 to the power of. So I would get 20,799 milliwatts, 20.799 watts. Then I need to convert that into a voltage using that resistance. So then I'm going to divide by the 10 kiloohm. And then square root that. So I'd have to have 45.6 millivolts coming in. What do you think? I mean, you can see when the input and output voltages aren't balanced, it's really tough to deal with. Because you got to deal with voltage on the back end and wattage on the front end. Everything we're going to do in here will be